algebra, vector algebra. We'll stay in R3. As I said, from this point on, pretty much discussion is in R3. Let's do some notations. Actually, let's change to Rn, like so. We're going to say generic vector in 2-dimensional will be V sub 2. Okay, so V sub 2 is the set. It's actually the set of all vectors in R2. Likewise, V sub 3 will be the set of all vectors in R3. And if you go down the line, you can go ahead and do V sub n, and that will be the set of all vector in n-dimensional space. Okay, just so you know. Okay, an important note is to realize that there is something called the zero vector. Okay, the zero vector is the only vector that has no direction, and we denote it with 0 like so. And what we mean by that, zero vector in R3, if we'll be specific, is the vector 0, 0, 0, or 0 times I plus 0 times j plus 0 times k. It is the only directionless vector. When we add in 3D, we do it very simply, and this is true for 2D as well. So, for instance, if we have two vectors A and B, where A is the vector A1, A2, A3, and B is likewise the vector B1, B2, B3, then A plus B is the vector. Can I undo the split? Did I hear no? Okay, undo the split. When we add these two together, we add like components. Okay, so we had A1 plus B1, that will be one component, A2 plus B2, and A3 plus B3. And this is important notion, especially if you do the homework. That's how we add vectors. We know how to add vector graphically, right? Place the initial point, place the initial point of one vector on the terminal point of another. But when you do it algebraically, that's how you do it. And of course, in IJK notation, we'll have the same thing, like so. Okay, let me give you a list of algebraic properties that apply to vectors, very similar to what we learned in college, actually in early algebra. Okay, so we have the commutative property of addition. For instance, the vector A plus B is the same as the vector B plus A. We have associative of addition, so the vectors A plus B plus C, where we place A plus B in parentheses, we associate these two together, we can write it as A plus the association of B plus C, like so. Okay. the zero addition, A plus, remember that zero vector that I talked about? So the zero addition of, and the opposite addition, okay, A plus the opposite of A gives you the zero vector. Exciting, isn't it? Let's scalar of distribution of a scalar of addition. If you have scalar C, multiplied by multiplying the sum of the vectors A plus B, you can distribute over addition, so it would be C times the vector A plus C times the vector B. Another algebra property is another distribution. If you have, but this is scalar, the distribution of the scalar sum. You have two constants, C, or two scalars, C and D, that multiply the vector A, then you can distribute it as C times the vector A plus D times the vector A. Okay, two more. You can also, what should I call it? Is this associate, or I'm not sure how to call this property. If you have a product of two scalars, C times D, and this is associative property, definitely. You can associate it and say this will be the scalar C multiplying the vector dA, the scale vector dA, like so. So you can see how the associative property is working here. And the last one is the scalar identity. If you have a 1, the times A is the same vector. So most of this is trivial, but we need to go through this. Okay. The next topic is unit vectors.